Okay, so this is lecture 3 of Professor Kulkarni.
Okay, so we do have to go back to reflection functors. But there is one item that I want to get out of the way immediately. This is going to be useful for us and also for your Lee algebras uh, lecture series. So this is very simple. It's linear algebra. So I'm in a Euclidean space. That means I'm in a real vector space with a positive definite bilinear form. Okay. Uh, but please do not think of this as a dot product with respect to this, the standard inner product summation xi yi. It could be any positive definite bilinear form. Okay, so given this, we have a very visual picture of this. In this case, you will have orthonormal bases, you will have lengths and angles. So if you are given a vector, let's say alpha in V, which is not zero, then you can just picture that I would like to take the reflection in a hyperplane that is perpendicular to alpha. That means everything that is perpendicular to alpha should get mapped to itself, and alpha should get mapped to what? To minus of itself, right? So there is a very useful formula. So sigma alpha of x, and that is going to be x minus 2 times. So you see, this needs to be a linear map. That means that whatever I write should be linear in x. So this is what I do. Okay. Uh, this formula should really be fixed in your mind. All right. So let's examine this formula a bit. If x is perpendicular to alpha, that is, if alpha and if the inner product is 0, that tells me what? Sigma alpha of x is x, because the second term just dies, right? Whereas sigma alpha of alpha itself is what? Then you see this 2 over here works very nicely. This is alpha, and then alpha with alpha and the denominator, they just die. And so I get sigma minus 2, sorry, alpha minus 2 alpha, which is minus alpha, which is exactly what I expect a reflection to behave like, right? Okay, so please keep this formula in mind. It's going to be useful for us and also in your other course. All right, so let's go back and recap what we did. So the setting is Q is absolutely any quiver whatsoever. Only I have to have a fixed vertex I, which is a source or a sink. I will treat the two cases separately. And V is a representation of Q. All right. So if I is a sink, then I'm going to, if I is a sink, then I'm going to define a reflection functor called Fi plus, and the way it acts on V is as follows. Okay. So first, I'm going to change the quiver. In my original quiver, the vertex I is a sink, so all the arrows adjacent to it are going inwards. In the quiver sigma iq, whose representation this one is going to be, all arrows adjacent, all arrows incident on I are going to change their orientation. So this sink will change into a source in the new quiver. What's the representation itself? For every vertex that is other than I keep the vector space the same. And at I do something interesting. Okay, so let's look at this carefully. What I do is I regard this map, I gather all the neighbors of I. So that is all the vertices that which are connected towards I. I take the vector spaces, I take their direct sum. And I just take the direct sum of all the maps that are given to me in the representation to I. Okay, so that is the one that I'm going to call phi. Please keep this name in mind. The name phi for a while when we are talking about reflection functors will always mean this. Okay, so what do I do? Uh, I need reverse arrows. All the V's are going to stay the same. So I need to put something in the place of I. So all I do is I have chained all of these maps together. Uh, and I simply take the kernel of this composite map, which is what I've written over here. So in terms of the picture, what will happen is all of these arrows will reverse. And I will need to have something that goes into these vector spaces. So I will simply take the kernel of this map. So that is going to be something that maps in here. All right. So that is what I have put in slot I. Okay. So what are the maps? The maps in the new thing that do not involve the I, nothing changes. Notice that what has happened now is that earlier, whenever I had arrows from J to I, now my arrows are going to go from I to J. So I need to tell you what all of these blue maps are. Well, they are very simple. The vector space that I have written over here is a subspace of this direct sum. So I just take this subspace and I take its component maps, which is what I have written here. Is a projection from the kernel on the jth component. All right. So this is what happens for when I is a sink. And there is a completely parallel description for with, for when I is a source. So let's go through that very quickly. Now I call the functor fi minus. All the arrows are going out. So I need something where the arrows go in. What I do is I chain together all of these maps to get a map from Vi to the direct sum of all of its neighbor representations. Okay. And I need to put something on the other side. So I take this map, which I'm going to call psi. I take its co-kernel. So this co-kernel of this map is going to sit over here. And there will be a map from the direct sum to that co-kernel. So what do I do in the new representation? I need to have maps from Vj1 from the neighbors going towards I now. What do? I simply take every one of the neighbors and include it in the direct sum that I have made over here and just follow it with the quotient map. Okay, so this is what the co-kernel is. A couple of things to note. One is that something, so these two situations are going to now be related to each other. So pay attention closely. Once I make this change and get a representation of sigma iq, in this new quiver now, the vertex I is going to be a sink. Okay, so I can contemplate, for example, applying fi plus to this. With that in mind, let's observe something. Notice that in the new situation, the map that I got from, so remember this map I have called psi, whereas the earlier map I called phi, right? So observe one thing. In this new situation, the map phi that I get for the new quiver, the map phi that I'm going to get for the new quiver will be the direct sum of all of these chained together, mapping onto that. And that's going to be my new map psi for the new map. Sorry, that is going to be my bad. That is going to be the map new phi. And that map is now, I'm sorry, am I making a mistake over here? Yeah, so I made a mistake over here. That map is going to be onto. Just because you see what the map is, it is a map from the direct sum of all of these things onto the co-kernel of some map that is going into here. So this map is of course onto. Likewise, in the earlier situation, the representation that I replaced Vi by was this one. And of course, this representation is going to include in the direct sum. So when I take the changed quiver and take the map psi for that, it is going to be injective. Why are these observations relevant? Consider the following. In the original quiver, again observe this map phi. We explained at some length yesterday that in the original representation itself, if this map phi is not onto, then I can simply split off the co-kernel of this map, which will be some vector space, and put that co-kernel on vertex I and put zeros everywhere. And that will be a direct summand of V itself. Okay. So this, which is what I have written over here, that V is going to split off as the co-kernel of this map phi, which which is supported at I. And then there is this question mark, which I wrote as something over something yesterday. We will now be able to say what this is precisely. And this is going to be an exercise. This is going to turn out to be, I'm first able to apply Fi plus to V, and then the result I can apply Fi minus to V. That's what's going to be the split off as the direct summand. This is going to be an exercise. Okay, so let's see the parallel situation. What we are going to have is, once again, in the original representation, if the map from Vi to the direct sum of all of its neighbors, if this map is not injective, then just like before, we can split off the kernel of this map as a direct summand of the original representation, where I put zeros on all the other slopes. Okay, so that's what I've written over here. That the kernel of the map supported at I is a direct summand, and in exactly the parallel fashion, this is going to be, I apply Fi minus to V and then I apply Fi plus to V. So I will get this as a direct summand. Okay, so any questions on this? Because we are going to leverage everything that we said now into some key observations. Very good. So observe.
Can I just say that for me, at least, your video is off?
Oh, okay. So
yeah, your video is not.
Just 1 second, please. Okay, I'm sorry. Let me just see if I can do this quickly. Otherwise, 1 second. Okay, all right. I don't know how that happened. Has it come back on?
Yes.
I have one question. Can I ask?
Yes,
Hello?
please go ahead.
Actually, on the first part that you apply, first Fi minus V,
Okay.
the thing that is written here, you have written two direct sums. The below one.
Yes.
Yes. The first direct sum that you have written, first apply Fi minus V, then Fi plus. Fi minus V, we have seen Fi minus V, each component of that, like Fi minus
Yes.
VL. So,
Yes.
but when we are applying Fi plus, then we have to apply on each component separately, like Fi minus or Fi plus.
Yeah, but okay, so I'm not sure I understand the question, but let me say, see, Fi plus and Fi minus are functors. That means that
Yes.
they take the entire vector space, the entire gadget, all the vector spaces at all vertices and the maps, and do something to it. So let's just look at this for a moment and see what's going on. So for example, what is this going to be? Fi plus of Fi minus of V. Well, Fi minus of V is sitting here in front of us, right? The only thing, I mean, this is only a local picture, what is happening at I. Everywhere else, it's the same. So what does it mean to say that I apply Fi plus to that? Okay, so let's go back and see what Fi plus does. What Fi plus does is that it chains together all the maps that are mapping into my hotspot, and then takes the kernel of the direct sum of those maps. Okay, so keep that in mind. Let's do that over here. The representation to which I'm applying Fi plus is not the original one, but it is this one. So this is the hotspot I. What is connected to it is still the same neighbors as I started with. So I'm going to take their direct sum. Okay. I'm going to take their direct sum and I'm going to take the map onto the co-kernel. Notice that this map is already onto, which is what this observation is. So I'm going to take the kernel of this map.
Oh, okay, I understood. Okay.
Right.
Thank you.
And you see, when I take the kernel of this, when I take the kernel of this map and I'm going to put it over here, right? I'm going to put it in. I'm going to put it in this slot. Okay, so Sorry, let me just gather my thoughts for a moment. Yeah, so let's go on. So the upshot is the following. You see, if my so until now the representation, there is absolutely no restriction on the quiver or on the representation, nothing. Okay, except the fact that I has to be a source or a sink. Okay, now let's see the following. If the map phi is onto, that means I go in the original situation, right? Which means that this map phi is onto. All right. So if we apply this observation, what it means that there is no co-kernel. Yes. The co-kernel is 0. The map is onto. So if I apply the construction, then going by the exercise, I'm going to, if I apply fi minus to this, then I'm going to recover the original representation. But let's try to see this directly. This is a very simple issue, really. So the issue is the following. Okay, essentially what is happening is the following. Suppose I have, let's just do a completely different situation. So let us suppose I have a map of vector spaces. Let's just call them A and B. Okay, and let's see what essentially is happening schematically when I do this. When I do fi plus, I'm replacing this B by the kernel of the map, right? So from this, I'm going to get A. And remember, my assumption is that this map is surjective. So I'm going to replace B by the kernel of F. Okay. That's what happens when I take Fi plus. But what do I do when I take Fi minus? When I do Fi minus, I take this map, which is always injective, we saw. But the point is now I take the co-kernel of this. So what does it mean to take the co-kernel of this map? I go back. So I take this map and I write co-kernel of I. So what is the co-kernel of I? That's precisely A modulo the kernel of F. Yes. But what is A modulo the kernel of F? It's the image of F, right? However, I took the map F to be onto. So I just got B back. The general situation is exactly the same. There is no difference whatsoever. Which is isomorphic to B if F is onto. So this is what gives me the first observation. So this is what gives me the first observation, and the second observation is exactly the same, right? Okay. Now I leverage this further. Now I'm going to make the assumption that V is indecomposable. Okay. So let's see what happens. If V is indecomposable, I'm going to take the situation where I is a sink. We saw so we have to keep on remembering exactly what this construction is. Okay, when I is a sink, I take the direct sum of the maps from the neighbors to Vi, and I take the kernel. Okay, so let's keep that in mind. So we saw that if your representation is the simple module at I, there are no neighbors. I mean, all the neighbors are 0. So when I take the direct sum map, that map is 0. Its kernel is also 0. So we saw that the reflection functor just kills this simple module. But just notice what will happen. V is indecomposable. That means that the map phi, that is the map from the direct sum of the neighbors to Vi, has to be an onto map. Because if it were not onto, then I would have just decomposed the original representation by putting in the co-kernel in slot I and 0 everywhere else. So that means that if I do not have, so that means that if V is okay, if V is not equal to SI, then what it means is that there must be some other modules. Okay. But no matter what, the map phi has to be onto. You see, if you want, I can go back to the original situation. V is going to be a direct sum of two things regardless of what happens, correct? So if V is indecomposable, either the first one must be 0 or the second one must be 0. Yeah. So the first one being the 0 is precisely the situation where I have SI. But if the first one is non-zero, if the first one is non-zero, then the second one must be 0. That means that there is no co-kernel. And so I'm in this situation. All right. But now let's take a look at what happens. This Fi plus V, I'm claiming is indecomposable. This is a new thought. All right. So we are saying that if my original indecomposable module to which I'm applying the reflection functor is not the simple module over there, then after applying Fi, so it's a dichotomy. Either applying Fi plus will kill it or keep it indecomposable. Okay. So let's see why this happens. This is not difficult. So I'm now going to be in the situation where the map phi is onto. So I need to show that this is indecomposable. So the proof I have written over here. So okay, let us suppose that it decomposes. So it will decompose into x direct sum y. Yeah. But notice that the maps, yeah. So after doing Fi plus, remember that I have gone into this situation. I've gone into this situation over here. And the new map psi that I have obtained is injective. Yes. So in this representation, the map psi is injective. So if I apply Fi minus to that, let us examine what happens. So in Fi plus, the map psi is injective, and x and y, the putative direct summands, are sitting inside that. So the maps, okay, I should write this down. The map psi for all these three representations are injective maps. And we just saw that if the map psi is injective, then if I apply Fi minus and then Fi plus, I get back the same thing. So this x, if I apply Fi minus to that and Fi plus to that, I'm going to get x. In particular, this Fix has to be a non-zero thing, because after applying Fi plus, I'm getting back the original non-zero thing. So this Fi minus x has to be non-zero. I'm assuming over here, for the sake of contradiction, that this x and y is a non-trivial direct sum decomposition. So that means Fix is non-zero, and likewise Fiy will also be non-zero. But look now, what happens? If I apply the functor Fi minus over here, then Fi minus of, it's very easy to see, by the way, that the functors, I asked you to check that Fi plus and Fi minus are functors. That requires a little check. But the fact that Fi plus and Fi minus preserve direct sum is even easier, because everything just splits up, you see. So if I take Fi minus of left hand side, then I get Fi minus of this direct sum, which will give me Fi minus x and Fi minus of y. But remember, this Fi minus Fi plus V is V itself, because I'm in this situation. So what did I obtain? If Fi plus V decomposed into direct sum, then just by coming back by means of Fi minus, I will get a direct sum decomposition of V. And these are non-trivial, as we just observed, which is a contradiction. Okay. So something very interesting happened over here is that, and this is the upshot. So what are we saying? That there is a bijection between, so it falls into a clear dichotomy. If I have a quiver Q, and let us say the vertex I is either a source or a sink, doesn't matter. Let for definiteness, let's take a sink. Then the indecomposable representations of Q and those of sigma IQ. that is the quiver that I obtained by reflecting the arrows at I, they just pair up. In what fashion? If I have Si, then it dies. Okay, but there is of course another Si sitting on the other side. So you could artificially just pair up the Si for Q with Si for sigma IQ. But when you set that aside, the rest of it just pairs up functorially. If I start with an indecomposable representation V of Q, then what this is telling me is that Fi plus V is also indecomposable over here. And Fi minus of that indecomposable is also going to bring me back exactly to the same one. That's just what we observed over here. So these are just mutually inverse functorial isomorphic, functorial bijective correspondences between indecomposable representations of Q and indecomposable representations of sigma IQ. Okay, so this is a key point. Any questions until now?
Yeah, I have one. May I ask?
Yes, please go ahead.
Oh, so I don't still understand why this V is equal to Fi minus Fi plus of V.
Correct. Okay, so let's go back and see this. Okay. All right. So what you would like to discuss further is this, correct? So remember, this
Yes.
result had nothing to do with indecomposability per se. All we said is that if the map phi is onto, then Fi minus of Fi plus V was V itself, isomorphic to V. Okay, so let's go back into that once again. I'm just going to look at this picture once again, right? So everywhere away from I don't have to bother, right? Nothing is changing. So it's only at I that I have to look. So the original picture at I is over here. When I apply Fi plus, this is the picture that I get, right? Okay. What does it mean now to take Fi minus of this? What is the definition of Fi minus? The definition of Fi minus says take the vector space at I, look at all of its neighbors, take their direct sum, and take the map from this to the direct sum and take the co-kernel. Okay, so let's examine that. The map, this is precisely the map that I have written over here. Now, what is this guy over here? This is really just the kernel of the direct sum of these maps, no? So what were these maps? These were maps from I'm going to erase this because I'm essentially going to do the same thing. Okay, so I have originally Vi, direct sum of Vj's. I'm not going to write the arrows. And I have this map. I have this map phi. Now I have taken the kernel of this map. Okay. And this kernel is the thing that I have put in this slot. So let's write this over here. Okay. So remember now in the new quiver, this K is just another name over here, right? In the new quiver, if I want to apply Fi minus, then what do I have to do? I have to take the vertex I and see what is sitting over there. Remember, what is sitting over there is K. And I have to take the map psi. But the map psi is just chaining together all of these blue maps, right? So when I chain together all of these blue maps, that is really just inclusion. So this maps psi in the new quiver is just the inclusion map. Okay. What does Fi minus ask me to do? It asks me to take the co-kernel of this map psi and put it at vertex I. However, what we just saw was that if the map phi is onto, I mean, that was our hypothesis, right? If the map phi is onto, then all I am saying is that direct sum of Vj modulo kernel of psi is precisely going to be again isomorphic to Vi. It's like saying I take the kernel of an onto map and I take the co-kernel of that map. I'm going to get the original thing back.
Yeah, now I understand. Thank you.
Right.
I think
Okay.
so.
But
Is it
yeah.
like, sorry.
Yeah. Sorry, but one thing. So thank you for that question, because I did lie here a little bit by omission, in the sense that all I checked was that if I turn the handle and turn the handle again, then the vector space in the slot is the same. Well, I mean, not same, but isomorphic. Strictly speaking, I have to show that the entire module is isomorphic, right? That means I have to also worry about a compatible isomorphism. Yes, the maps everywhere else are going to be identities, but I still, strictly speaking, should check that the representation that I have so obtained is not really just an isomorphic vector space in that slot, but it really is isomorphic as a representation. So I should say that that's a check that one should carry out. Okay. So I will just write it over here.
One more small thing.
So let me just write this, please. So check isomorphism of representations. Okay. Yes.
So see, your argument just is transfers to the first isomorphism theorems, right?
Exactly.
And
the basic isomorphism theorem, and it's go for the other situation, it's going to be exactly the same. Yes.
it's going to be exactly the same thing, right?
Yes. Yeah. So co-kernel
But
of
you
the
are
kernel
first
and
going to
kernel of co-kernel, if you will. Yeah.
okay. And one more thing is, like, if you take an indecomposable which is not supported at a source or a sink, which is somewhere far away, supported somewhere far away, then
Yes.
your bijection, it maps identity, right? That's just.
But now no. So this really
Is
has
that
to be seen. This has to be seen a bit carefully. If your simple module K is sitting at a place which is not adjacent to I, then
Correct.
nothing will change.
Yes.
However, if the simple module K is supported at a neighbor of I, then interesting things will start happening, as we saw yesterday.
Yes.
In the problem session. So
also the indecomposable,
and in fact,
right?
so let me just say, but this is precisely the thing. No, now we have a new toy. What we just observed is that if I start with indecomposable representation, even if I start with a simple representation, and if I just start applying reflection functors to it, I will keep getting indecomposable representations as long as they do not die of different quivers. That is okay. But but maybe somehow I can come back to the same quiver. We will examine all of these issues. Okay.
I have
But today's agenda is something else. Yes.
One more question. Like, we know if we take a simple, we may get the indecomposable. Is there any way we do see last tutorials exercise that some indecomposable turns to be a simple or something like that? Is
Yes.
there any?
Yeah.
What is the situation?
Yeah. So let me sort of not go into this, because all of these things are going to come. All
Okay.
of these things are going to come.
Okay.
All right. So yeah. So the next thing is all right. So this upshot. This is an interesting point that. All right. So now the scene of action is going to shift a little bit. So let's get there. And in order to do this, what I would like to see is what is the dimension of this of the image, Fi plus V or Fi minus V, where V is an indecomposable representation and not the simple at I, because the simple will just die. Okay, so what happens to the dimension vector? Let's see that. Remember our sort of final goal that we stated, that there is that for nice types of quivers, for quivers of type AD, quivers of finite type, we are going to have a bijection between indecomposable representations and their dimension vectors. So we do need to worry about this. Okay, so think of the dimension of V as a vector in Z to the N, where N is the, sorry, I did not write this down, where Q is where the vertex set, I have just somehow numbered it from 1 through N, and I'm taking the standard basis, which I'm going to call alpha I. Okay, so 1 in I slot. Okay, so let's take this dimension vector d1 up to dn for some indecomposable representation. So I write it as summation di alpha I. All right. Okay. So what happens if I apply fi plus or minus? Of course, I can't apply this simultaneously, right? Depending on whether I is a source or a sink. But anyway, nothing happens to the dimension vector, right? It stays the same. So let's look at what happens in slot I. And for this, I should go back and look at this once again. The issue is very simple. I simply take the kernel of phi. Right? Now remember, because V is indecomposable and not SI, this map phi is onto. This is an onto map. So the dimension of the kernel of this is very easy to calculate. What do? I just take the dimensions of all the neighbors, add them up, and I subtract the dimension of I. Okay, so that's what happens for Fi plus. Let's see what happens for Fi minus. What do I do over here? Now I'm going to take the co-kernel of this map psi, right? So what does psi do? It again takes now the map from Vi to the direct sum of all the neighbors. But now I know that by my hypothesis, because V is indecomposable and not SI, this map is 1-to-1. It's an injective map. So if I take the dimension of the co-kernel, it is again going to be, or rather it is going to be the dimension of the target now minus the dimension of the source, but I get exactly the same number. The sum of dimensions of all of these minus the dimension of time. So I have written this down. Okay. So in slot I, what I get is the sum of the dimension of all the neighbors minus this. Okay. So I had half a mind to try to sort of worm our way to something, but I will not do that. So this is the story. What we are going to do is we are going to realize that this new dimension vector. Okay. So what is this new dimension vector? It is summation dl alpha L for all L other than I. But in slot I am going to write this. So you see, it just changes slightly, right? It changes only in slot I. So this should put you in mind about the observation that I made originally, right? Something about a reflection, where you keep the vector the same, except you change it by a certain multiple of a single vector with respect to which you are taking the reflection. Okay. So something very similar is going to happen. I'm going to define an operator on Zn, sigma I, which is going to be a reflection, by means of some bilinear form that I will define, such that the sigma I of V will be exactly the same formula as before. Okay. So we will define such reflection via suitable bilinear form on Zn. Okay. So I'm not sure whether we will get to this, but in what form. But it's not a difficult exercise now for you to try to guess what this form is going to be. Okay. And formally speaking, I wrote this alpha I, but in our case, it is just going to be a unit vector. So you can just delete this. Okay, so let's see how this goes. And the action is now going to shift. Our focus is now going to be working in Zn, which I will think of as the space, not just of dimension vectors, but the entire sort of lattice in which the dimension vectors are sitting. They are sitting in the non-negative cone. All right. And I'm going to do something over there. Okay. So now until now there was no restriction on the quiver. Now I'm going to take an acyclic quiver simply because then I do not have to worry about whether I will be able to apply reflection functors or not. I will always be able to find a source or a sink. Okay. All right. And so the quadratic form, I'm going to define a quadratic form for this quiver from which the bilinear form will come. And this quadratic form is defined in this fashion. So by the way, the quiver is acyclic, so there are no loops at any vertices. So what happens is that at every vertex I, this is the definition. So let us see what happens. A quadratic form, if you want, is just a homogeneous quadratic polynomial. You can think of xi's as variables. Okay, but here x is going to be an integer vector. So what you do is for every vertex, I have vector x1, x2 up to xn. At every vertex, I just take the square of xi and I add them together. And for every edge I to j, I write xi xj. And I take the sum over all such things. Now notice I did not say arrow, I said edge, because notice what happens. For example, in the example that I have written down, this is the quiver of type A3 with one orientation. So what does it say? Take the square at every vertex. So my vector, so remember here that this is the quiver, but there is some vector here sitting associated to it, right? With slots 1 through n. So these are integers. You can even take them as real numbers if you want. Here it doesn't matter. So for x1, x2, x3, I just add their squares at each vertex. So that is x1 square, x2 square, x3 square. And for every edge, so there is an edge between 1 and 2. So I subtract x1, x2, and likewise I subtract x2, x3. So the thing is that I did not put an arrow over here because the arrow doesn't matter, you see. If I reverse the orientation, nothing changes. Okay. All right. So where did I just pull this out from? There are two different connections to make. One is that we will see that this the bilinear form associated with this quadratic form will be very closely related to the formula that I obtained for the dimension vector. But there is a completely separate connection which we might have time to get to at the end, which is that if I apply this quadratic form to the dimension vector of M, where M is a representation, then that has a homological meaning. Okay, so all right. So now we have to talk about some notions about quadratic forms. So a simple definition: a quadratic form is called positive definite if on every non-zero vector, if I evaluate the form, it will be positive, and it's called positive semi-definite if I have weak inequality for every non-zero x. Okay, so why are we getting to this? Because this is our goal. It says that for a quiver Q, this is a question that we asked. No, we wanted to classify all indecomposable representations for any given quiver. Now that's too difficult a problem for an arbitrary quiver, but for quivers of very special type, type A, D, and E, which we will see momentarily. Those quivers are of finite type. That is, there are only finitely many indecomposable representations. But in fact, the converse is true. That is, if the quiver is of finite type, then its underlying graph must be of this type, ADE. Okay. So in order to connect 1 and 3, the equivalence, we will go through the associated quadratic form for the quiver. So 1, 2, and 3 are equivalent. And the quiver now, the representations of the quiver will recede just for some time. What we will do is we will first show the equivalence of 2 and 3. Okay, so this work is going to be happening essentially in Z to the n. Okay. All right. So what are these quivers of type ADE? So AN, once again, the orientation does not matter, because remember, the quadratic form does not depend on the orientation. It depends only on the graph. So type AN is simply n dots strung together. N, the index n in all of these is the number of vertices. Dn is going to be this. Okay, so this.
So is it
here
all? It is also the labeling of the vertices doesn't matter, right?
the
Or
labeling of the vertices does not matter, but it sorry, that was again a mistake. I made a mistake, and correcting it I made another mistake. Okay, so all right. But this is some kind of standard labeling. Okay, so the labeling doesn't really matter. So this is type D. Notice a particular one when the reason for taking n at least equal to 4 is that if n is up to 3, then you are just going to recreate type AN. All right. I should say one thing for a for a connected quiver. The graph should be connected. Yeah. Okay. So notice a very special case for type Dn. When n is equal to 4, you are going to have 4 vertices with so 3 of them will be connected to one central vertex. So that produces some additional symmetries. All right, and then you have these special exceptional ones called E6, E7, E8. E6 is symmetric. You see there are 5 vertices in a line, and from the middle one a line sticks out. E7 cannot be symmetric like that. So you still have a line sticking out from 3. But E8 has a chance to be symmetric, but it is not. Remember that you still have the vertex, the trivalent vertex, where there are 3 spokes coming out. On one side you have 2 vertices. On the other side you have 4 vertices. Okay, so that's what these pictures are. As I said, we'll first prove the equivalence of number 2 and number 3. That is to say that the quadratic form is positive definite if and only if the graph is of type A, D, and E. And in order to do this, we will actually take help of other diagrams, which are called the Euclidean diagrams. So what we will show is that the form is positive semi-definite if and only if either it's positive definite, in which case you will get the types A, D, E, or you get these extended Dinkin diagrams or affine or Euclidean diagrams. So notice what they are. Yeah. So so all I have done is put tildes on the vertices. So I have A and tilde. I take all those n vertices and I simply make a cycle out of that. For D and tilde, now it's a symmetric thing. So what I do is, so the graph over here, this part is really the same, but I have just made this slanted because I have put another vertex here, label n plus 1. For E6, E6 also is symmetric, even though it has you can see that now this vertex 3, it has 3 spokes coming out of it, and all of them have length 2. So that's what E6 is. E6 tilde. E7 tilde now becomes symmetric because I put another vertex over here. So now I have 3 over here and 3 over here. And for E8, on the other hand, I put something on the other side. Okay. All right. So our theorem is going to be these quivers, the extended, the affine Dinkin diagrams, they all the affine diagrams, they also have representation theoretic significance, that they precisely correspond to those quivers whose representations are tame. Okay, so that's a term that we will introduce, maybe. But our main goal is to prove Gabriel's theorem, as stated above. Okay, so from this Q, which is a quadratic form, I'm going to get an associated bilinear form, and that is very easy to obtain. So what do? I take Q of x plus y minus qx minus qy, and it is not difficult to see that this is a bilinear thing. So this is a bilinear form. So this is a small check. You can of course recover Q from the bilinear form by applying by taking the form of x with itself. And so what? Okay. So one thing. So let's just do this small calculation. So is it clear? So what happens if I take the form with itself? Let's just say I get q of x plus x, that is q of 2x, because it's a quadratic form. When I multiply the argument by something, the form scales by a scalar. So this is going to give me q of 2x is going to be 4 times q of x, and I subtract q of x twice, that will give me 2 times q of x, and that's the reason for this. It's completely standard. Okay. Yeah. So our strategy to prove the equivalence 2 and 3 for, to locate, to detect precisely those quivers for which that are of positive definite type, is to first solve the problem for positive semi-definite. And for this, we are going to have a key lemma. So this is what I have written over here. So Q is a connected quiver. I will be able to detect whether Q is positive semi-definite by means of a very special vector D. Positive semi-definite, but not positive definite. Okay. So what am I assuming? So I'm assuming that there is a special vector D such that when I take its bilinear form with every vector, I get 0. So in particular, such a form cannot be positive definite, right? Because D with everything is 0, in particular with itself. So existence of such a vector means that the form is not positive definite. However, just having this vector tells me that the form is positive semi-definite. By the way, such vectors are called the radical of the form. So i.e. a radical of the form. If not only that, if I have such a vector D, then it cannot be 0 in any one of the slots. That is, in every slot it has to be non-zero. And moreover, what we see is that the radical is really one-dimensional. That is, radical is generated by a single vector. So if Q of okay, so
I'm sorry, I didn't get why that directly implies positivity in the other. So I understand semi-definite, but it could be indefinite or something like that, right?
no, but this is a claim. No, we have to prove this. So this lemma is going to require some calculation. It's some argument. I'm simply making a claim.
Okay.
I'm simply making a claim. So you see, having such a vector is a very special thing, right? It's going to give us all of these things. Just having such a vector means that the form is positive semi-definite. Not only that, D is non-zero in every single slot. And moreover, if the quadratic form vanishes on, notice the quadratic form certainly vanishes on D, because the quadratic form is just half of D with itself, right? So it vanishes. So what it says is that if the quadratic form vanishes on any vector whatsoever, then it has to be a rational multiple of the given vector D. Okay. So so how is this going to help us? Because now there is calculations, and these calculations I want you to do for yourself. Okay. So the way this is going to help us is the following. If I want to show that these, so just see the strategy, because now then there is a fair amount of just calculation and working out. The strategy is very nice and not difficult. So my claim is that all of these, that these are precisely the positive semi-definite ones, correct? So in one direction, I need to show that these are positive semi-definite. This lemma just gives me a very easy way of doing it. Namely, I just have to find a magic vector for each one of these, right? So I should just label each vertex with some integer, such that if I evaluate the quadratic form, I get 0. That is, if I evaluate the bilinear form with every vector, I'm going to get 0. This is a concrete calculation which one can just carry out, which I'm going to ask you to carry out. Okay, so this will show that these ones are positive semi-definite. Okay, but how will I show that these are the only ones that are positive semi-definite? Yeah. So this will come about as follows. For this, we are going to use the second part. What this says is that if the form is that if I have something that is positive semi-definite, then I will be able to then. Okay, so just give me a moment. Where's this going to go? Yeah. So basically, what are we going to do? We are so this argument is a little more involved. But what we are going to show is that we are going to use the fact that if I have a special such x, then it has to be a rational multiple of the given d. And if the given d and such a given d has to be non-zero in every slots. So if I have something, then I will try to locate a sub diagram in which I will get a positive vector, in which I will get a vector in the radical, and then I will show that, look, if this works, then everything else, if I have just put zeros over there, then it is going to give me a contradiction to the fact that everything has to be zero if I have such a vector. So once I have reduced to the case of positive semi-definite, then I will prove the result by saying that, look, if a quadratic form, so now how do I show that the form is positive definite for these ones? There are two different ways to do that. One is I simply add the extra vertex, and I use that extra vertex along with parts B and C to show that the form cannot be positive semi-definite on these. Because if the form were positive semi-definite, then I can regard, for example, this AN as a sub-diagram of AN tilde. But I know that any vector for which Q vanishes must have its support on all vertices, in particular the vertex n plus 1, which will contradict my assumption that AN is positive semi-definite. That is one way. Another way is that I can directly take the bilinear form, and we have Sylvester's criterion to show that a bilinear form is positive definite. So I simply write down the matrix of this bilinear form, and I calculate all the principal minors, and I show that those principal minors are positive, which then means that the form is positive definite. So one can do either one of these things. Okay, so with this in mind, let's now start the work. Okay. So this is a long calculation, which essentially just one does as an algebraic exercise. So let me just try to reproduce that. Okay. So here's how it goes.
Hello, sir.
Yes.
So I have a question.
Yes.
So this is the type of D4. Suppose you take n to be 4.
Okay.
So is that D4 has some special property? Because it's, if you take the automorphism of that D4, it's isomorphic to S3, but other quivers are not like.
Yeah. So D4 is a special type. You get more symmetries.
So is there in some special property of D4 type quiver? There.
Well, I mean, okay. So I'm not really sure what kind of answer you're looking for.
Okay.
So does anyone have anything to say? Amit, is there anything particular that you can say about representations of D4 that is different from other Ds?
No, I mean, we are looking at an aspect which doesn't talk about symmetries that way.
Okay.
Oh, okay. Thank you.
Okay, but certainly if you go in Lie theory, then the D4 type has extra symmetries, which manifests itself in some ways. Okay, so
Thank you.
all right. So one thing that I'm going to do is so just produce requisite D. So check following vectors D work. Sorry, not so. This is not the proof of the lemma, but let me. So specifically follow for affine type, and I don't want to spend a whole lot of time on this. So I'm sorry, I'm just going to change these. So now these are going to be the labels of these. Okay, so here it is very easy. You just put all the ones over here. So the vector is just all ones. What you have to do is you have to take the quiver, take the corresponding bilinear form whose matrix you should write down, and check that this particular vector really kills every vector. Okay. Then for Dn we have the following. Yeah. So these become ones, and the inside is the chain is all twos. So this is 1 1 1, and you just have twos all the way. Okay, for E6 we have the following. So this I'm afraid I do not know by heart, so I just have to copy this from. All right, so 1 2 3 2 1, and of course it's going to be symmetric. So E7 has or rather E7 tilde. We have again, this is 1 2 3 4 3 2 1, and then the 4 goes to 2. And for E8 we have the following vector. Oh, this is funky. 2 4 6 5, and then 4 3 2 1, and then the 6 gets connected with 3. Okay,
I'm sorry. I just lost. What is this? What is this numbering?
yeah, correct. So let me. So this is not a numbering. So what is labels? Let me write this here. Absolutely right. Labels give special vector D as in the lemma. So should we carry out one of these calculations? Maybe type A is very easy. Look at the lemma. What it says is that I have a connected quiver. If I am able to find a D such that the associated bilinear form of D with everything is 0, then this quiver is positive semi-definite. Okay, let's just try to do this for AN.
One more thing. Can you just go up? No, this was kind of quick and slick here. What is the tuple that you are making in Dn? Because the original numbering is now gone, and
Yeah. So
the D I am not able to write.
Correct. So what this is the labels of the vertices do not matter at all. So let's just recall what we have. So where is that quadratic form? So remember, I defined a quadratic form on I defined the quadratic form on n dimensional lattice, if you will. So this has this has n vertices. So this gadget over here is something that takes n integers and produces a number. Therefore, its associated bilinear form is going to be a bilinear form on Zn. Associated bilinear form on Zn. N is equal to the cardinality of Q naught. Okay. So the lemma says that, so this is the space in which we are working, the abelian group Z to the n. This is a lattice in which we are working. If you want, think of it in Rn. So we are saying that so there is a bilinear form, associated quadratic form. We are saying that if I am able to find so the form that is defined over here, this bracket, this is the one that is coming from the quadratic form. We will soon write down an explicit formula for this. I think that may be better. So what this lemma is saying is that if I am able to find a vector D such that its bilinear form with every x is 0, then that is enough to show that the quadratic form is positive semi-definite. So this is giving me a key to show that all of these affine quivers are positive semi-definite. What do? I take n plus, so in each case I'm taking n plus 1 dimensional vector space now, because this an tilde has n plus 1 vertices. So so all that this is saying is that take the vector 1 1 1 1 1 in each slot n plus 1 times. And likewise,
sorry to stopping you. I remember in E tilde and E7 tilde, E8 tilde, there was some blue arrow that you draw earlier. Now it was missing.
Yes. Okay, sorry. Right. No, the arrow is not missing. I've simply made those arrows black. Notice that this E6 had 6 vertices earlier, whereas now it has 1, 2, 3, 4, 5, 6, 7.
Thank you.
Okay. And likewise, E7 tilde has 8 arrows, and E9 tilde has, and E8 tilde has 9 arrows. So the numbers that I have drawn over here are the special vectors D as in the lemma. I think we should really just check this. Okay. Check that the so for type A, what is the form? So take a couple of minutes and try to work out what the form is. So Q of x is going to be summation xi square minus, and so you see now I have a chain. 1 is connected to 2 is connected to 3 is connected all the way to n plus 1, which is connected back. Perhaps we should take a okay, minus x1 x2 minus x2 x3 minus x3 x4 all the way up to xn xn plus 1 minus xn plus 1 xn. That is the quadratic form. So check that the associated bilinear form is going to have the following matrix. You have 2's on the diagonal and minus 1's on the so this is of type A. So just do the calculation. Let's see what happens. In fact, something is very easy, right? Just see that Q of x is equal to 0. For the Q, what is Q of D? That is
what is
Q
D?
Of so D is the given vector. So the D is the given vector is just all ones. So Q of 1, 1, 1 taken n times. What is it? This is the first check. But this is clear, no? How many terms are over here? I equal to 1 to n plus 1. So the first one
You are
will
doing
have...
type A tilde, right?
Sorry, yeah, thank you very much. Thank you.
Then it's
For
0.
type A, yes, exactly. Right.
And
That was a
also
mistake.
xn, x1 at the end.
Yeah, sorry, the last one.
xn
Yes.
plus 1, x1.
X1, thank you. So it's a circular one, yes. Okay. And so this is very easy, I mean, so I'm going to have 1 squared, I'm going to have n over here, and each one of these is going to give me n. So this is just 0. And so in fact, now you should just check that so now it's a matter of check, which I will leave for you to do. That calculate the associated calculate the associated bilinear form and show that d of x is equal to 0 for all x in z n plus 1. So check this. Okay, so now let's take a look at the proof of the lemma. So this will be some calculation. So essentially, I'm going to reproduce this calculation. There is one kind of key thing to do over here. Okay, so let's try to do that calculation. So notice that what I have is d with everything is 0, right? So d with each alpha is also equal to 0 by hypothesis. What does that give me? So yeah, but I do have to calculate this form, no? So which I did not do, which is a bad thing. Yeah, so check. That this means that. So perhaps is this something that we can leave for the tutorial? This is.
I have one more small issue over here. See,
Yes.
this alpha I you have defined only for a source or a sink. That needs an orientation.
No. No.
Right?
Let me go back. So okay, I think you are. Okay, now I understand. Yes, that is true. But whatever I am doing over here, everything that is being done over here is for a graph. There is no quiver or representation. There are no directions.
But then what is alpha I?
Alpha is just the vector. Okay, so yeah, I hope I wrote this down somewhere. Yeah, alpha is just.
Oh, okay, standard basis.
Alpha is just the standard basis vector. That's it.
Okay, thanks.
So that's what it is. Nij. So this is Nij Ej, where Nij equal to the number of arrows, number of edges. Between I and j. So in order to do this, we have to make the bilinear form explicit. I'm sort of in two minds whether we should do this here or leave it to the tutorial. I think we should leave this to the tutorial. So there are things to check, which I will just say this is one check. There is a second check, which is going to be the following: summation xi square, I going from 1, 2. Yeah, so I should draw a line over here. So I'm not talking about any kind of specific quiver now. So my quiver now has n vertices, and I'm trying to give a proof of this lemma. And I'm writing down some key calculations that we should check. So one is that summation xi square, where I going from 1 to n. Is going to be, okay, so I'm going to write the first step, which is going to be summation I xi square divided by di times summation j less than I nij dj. What is this? This is something very easy. The only thing that I have done is that let's call this star, and I have used star over here. Okay, so first, provided each di is non-zero. So this is something that we do have to prove, which we will come back to later. So then the next calculation, which is check, which we will do in the tutorial, but I will just write down. So this is just plain algebra. And what happens is that this turns out to be summation summation I summation j less than I of nij di dj divided by 2 times xi square divided by di square plus xj square divided by dj the whole square. So this is just algebra. So this is the second check. Once I have this check, then there is a third check, which is the following. So we know what qx is, that is summation xi square over I minus summation over I summation over j less than I nij xi xj. So recall the definition of what the quadratic form was. Sorry, where did we write this down? Okay. The quadratic form was simply taking the sums of all the xi squares, and for every edge I am writing xi xj. So this is just a different way of arranging the edges, because every edge I want to count only once, no? So this sum over here should not be for all pairs distinct pairs I comma j, because each pair then will be counted twice. So the way to do this is to just take it in a directional way. For every I only take the ones less than that are the vertices that are less than it. Okay, so this one then finally becomes again check, which is just a straight algebraic calculation using the previous results. And this is the key point now.
Again, we have just taken the adjacent edges, right?
What do you mean adjacent edges? Edges. We are only taking edges. So this nij. So let me remind you what nij was. Nij was the number of. So where did I write this down? Nij is the number of edges between I and j. So you see the term xi xj will come nij times. No, I'm allowing multiple edges between.
Okay.
Okay. Right. So this just works out to be summation over I, again summation over j less than I of nij di dj by 2. And now comes the key point. By appropriate completion of square, xi by di minus xj by dj the whole square. Okay.
Sir,
All right.
here have we made a choice of d, the vector d already, or are we just assuming that we have found one and then carrying on the calculation?
Yes. So let us, I'm sorry, I should really have kept the, let us once again remember the hypothesis of the lemma. I have a connected quiver and I'm given a vector d, non-zero vector, such that dx is 0.
Oh, okay, okay, all right.
Okay. So I see somehow this is the thing. I am already given a magic vector d. And everything is happening under that assumption. All right.
All right, sir.
Okay. So given this magic vector, vector d, I have, I've given you sort of some algebraic checks to carry out, which we'll do in the tutorial. So the first one is, because d, the bilinear form of d with everything is 0, that is going to give me the first inequality. The first equality. Just directly plugging it in here is going to give me the second equality. I do need to show that every di is non-zero, which I will, if I have time, I will momentarily just justify that. That is going to use connectedness of the quiver. And now, by means of algebra, I check that I get this expression. Now, all I do is that the quantity that I have over here, you see, I'm simply going to plug in this quantity in the definition of qx over here. I'm just going to plug all of this in. And then you see, you can imagine completing the square. No, there are these two square terms, and then there are these minuses, you see. And here is nij divided by 2. Okay, so so an algebraic calculation is going to show that q of x for any x whatsoever, by means of the given vector, it is going to be this expression. Now it is a sum of squares. So upshot, q of x is greater than or equal to 0 for all x. Okay. Q of x equal to 0 when can q of x is equal to 0 happen? If q of x is equal to 0, then every square has to be 0, no? But that just means that all of these quantities xi by di and xj by dj, they all have to be equal to each other. Whenever there is, right? So they all have to be equal to each other. In fact, I don't even have to say edge here. But that just means that x1 up to xn and d1 up to dn are proportional in Zn. That just means one of them is a rational multiple of the other. Okay, so let's take a look at what let's take a look at our claim and what we have done. Okay, modulo the calculations. We showed that q is positive semi-definite, and we showed part C. What we did not show is part D, namely that di has to be non-zero everywhere. And it was required for us to do this small it was required for us to do this to do this manipulation when I divided xi square by di and just multiplied it by another expression by di. Okay, so just to recap, modulo the algebraic check and showing that each of di is non-zero, I have done the lemma. Is there any question until now?
Sir, I have a question. We are
Yes.
given the vector d, but then
Yes.
in that we were also asserting that all of its components are non-zero. So if
Yeah.
we're
Okay.
already given a
Yeah.
vector,
So,
then
yeah. So in order to do that, so in order for my algebra to be valid, I have to prove part B, which I have not done. Okay, so that's just the modular algebra. That is the last bit that is left. Okay, so so why is that the case? And that for that we are going to use the connectedness of the quiver. Just notice what we have done over here. Just look at this expression. I have time, 1 minute maybe. I have 2 minutes. Great. Okay, so just look at this expression. It says that each di, each component is equal to the number of edges times the component, the number of edges between that and adjacent vertices, along with the label that is given to the adjacent vertex, right? This is what is being done. Yes?
Yes, sir.
Okay, all right. So what now? Suppose some di is 0. What will have to happen? This equation means that so all the yeah, so just yeah, so I'm just thinking whether I need in the hypothesis that see, I would like to deduce from this that all the neighboring DJs are also 0. But why can't it happen that some of them are positive and some of them are negative?
Or you want to switch the role of INJ in that equation because
No. So remember the quiver has. I mean, I'm assuming that there are no loops here. So the J's are all distinct from I's. Okay. So what is the? Yeah. So somehow I want to deduce from this equation over here that if some di is 0, then all the neighboring DJs also have to be 0. And by connectedness of the quiver, that means that everything will have to be 0. But I assume that the vector d was non-zero. Okay. So why is this the case? Or do I need extra hypothesis that I'm forgetting? Okay, so this is a point that I overlooked. Okay, so does anyone have anything to offer? Because I'm kind of stuck at the moment. I'm just going to simply say that this equation star implies that each di is non-zero. Okay, see, all right, at least as far as our purpose is
I have a question. Like,
yes,
what
actually,
is alpha I?
so sorry, alpha is just the standard basis vector, just 1
Okay,
0
okay,
0 0 1
fine.
0 0 etc. Right? So yeah, so the first check is actually very easy because see in order to calculate d with alpha I just have to make explicit what the bilinear form is, and this formula will just pop out of that. There is really nothing to it.
Sir, since Nij denotes the number of edges, I mean, we can't really have that being negative, right?
I understand, but my question is why can't some of the DJs be positive and some of them be negative for things to cancel out? That's my difficulty. See, if it is part of my hypothesis that d is a non-negative vector, then the argument is done. And so at the moment, I'm sorry about this. To end on this and end on this note, we are out of time. So at the moment, I have to make the assumption in the lemma, and I'm going to say that D is a D a non-negative vector. So I'm going to write this in red as a sort of admission of my sin here. So it's a question mark. So D. Okay, so I will sort this out, but it's time to stop now. At the moment we have to sum up. At the moment we have proved this lemma with the assumption that D is a D is a non-negative vector. And in that case, the only thing that requires is just some algebraic calculations, which I have highlighted in three as three things to check, which we will check in the tutorial. So once this lemma is there, then we can just directly prove our the equivalence of 2 and 3 in our big theorem. So with that, let's stop.